Hello and welcome. In this tutorial, we're going to implement a reaction diffusion simulation in Max. This tutorial consists of 3 parts. In the first one, we're going to set up a texture feedback system, because to achieve this reaction diffusion effect, we always need to apply the same operation to the same texture. So the input of the next iteration is always the output of the previous iteration. Therefore, we need a feedback loop. Then in the second part, we're going to implement the actual reaction diffusion code. And in the third part, we're going to introduce a mask so we can apply this reaction or this effect to different kinds of input images. Okay, let's start with the first part, setting up the feedback system. So I already have a jit.world here as our rendering context and a jit.p window to monitor what we're doing. So I will use a jit.gl.pix.codebox object. Then we need one texture as an input. Let's make this full HD, a depth 0, and let's say the type is float32, which is always a good idea when working with texture feedback. Okay, patching this in here, then I will use a jit.bang, which bangs this texture on every frame. Then I need a second one as an input here. I guess I'll do it like that. And then, yeah, the output comes in here. So we have our final output here, but we're also feeding it back into the whole thing. Okay, this is essentially our setup, except for, okay, no, I will do this later. Let's move on to the second part, which is implementing the reaction diffusion. So I got the idea for doing this because there is a great coding challenge on the reaction diffusion chemical reaction code, so to say. And Dan Schiffman is referencing a great article by Carl Sims. And I will also use this and kind of build my code on what we have here. So what I will do is I will make a screenshot, then drag this in here, and then we can work with this. Okay, because what is essentially happening, or what we're simulating here, is a chemical reaction. So we have a chemical A and a chemical B, and A is added to B, and then they react with or to each other. And there's also some diffusion happening, and some of B is going to get removed. And yeah, we're going to implement this in here now. Okay. How are we doing this? Maybe we can just go bit by bit. Okay, so previous values. So, okay. This A is the new value. So we can do something like next A. I will set this to 0 for now. And then we have next B. So this is going to be more or less our output. Then we need our previous values, A and B. I will just call this previous A, which is going to be the input of this texture. So previous A is the X component of input 2, and previous B is going to be the Y component of input 2. So we're not going to use this input. I mean, we're using this input like to initialize the whole thing, because jit.gl.pix always takes the dimension of what's coming in the first inlet, and also always starts the calculations when the texture for the first inlet is banged. So we need this to get everything going, but then we're using the second one for a feedback loop, and also the second one will initialize the whole thing. But you will see in just a minute what I actually mean by that. Okay, then, we have A equals this A plus, then we have this diffusion for A and diffusion for B. I'm going to create a param for this, so dA. So this is the diffusion parameter for our substance A, and here we have the diffusion parameter for our substance B. And I think, here, maybe we can also copy this and put it here. So typical value for A would be 1 and for B would be 0.5. So we can use it here. Then we have this, this is the diffusion rate. No, this is the diffusion rate. Then we have this 2D Laplacian functions. What this does is we're looking at neighboring cells and creating like a weighted average. So for each cell, we're looking at what are the neighbors doing and how will this affect the current cell we're looking at. So to do this, I will create a variable, let's call it lap. So we have, this is the difference between the average of nearby grid cells and this cells. So we can start with this cell. So because we're looking at the difference, we can say, okay, we have minus input 2. So this is our current cell, and then we'll just add on to that. So we will add the cell to the left of it. So I will say nearest. So we're sampling the cell to the left of it into normalized coordinates. Oh, to look at the next cell, we need to know the size of one cell, so the size of one pixel. So let's create this variable. Let's say pixel equals 1 divided by the dimension of the whole. So we can say, we can use this in here. So yeah, we're sampling it at its normalized coordinates plus an offset. So we're starting with going to the left, 0 in y direction, and then we're multiplying this by the size of one pixel. Then I will also say bound mode equals mirror. So we're not clamping anything, but when we're at the end of our texture, we're just mirroring it back into itself. So we're adding the left neighbor here. Then we're adding the right neighbor here. Then we're adding the neighbor above. And then we're adding the neighbor below. we also need the diagonals. So this would be on the top right. Bottom right. Oh no, didn't mean to do that. Then I can copy this. Then we have let's wait. Now I'm confused. Let's go over this again. Okay. So this is at the top right, then this is at the bottom right, this is at the top left, and this is at the bottom left. Okay. Should be fine. But as we're taking more or less weighted average, we also have to multiply this by some weights. So we're not taking all of the cells, or we're not taking the whole cell into account, or the whole of the neighboring cells, but we're applying some weight. So for the cells that are like direct neighbors, we're multiplying this by 0.2. And for the cells that are on the diagonals, we're multiplying this by 0.05. Okay, so, and then the whole thing should add up to 1. So this is 0.8, and this is 0.2. And so we're essentially saying, okay, we're using the average of our neighbors and then subtracting the cell itself. So now we have this thing. Then we have A times B squared. So this is kind of the reaction part of it all. Okay, I'm again running out of space. So I would just create a variable called this reaction. And yeah, A times B squared is essentially A times B times B. Now we have this part. And then I guess we have to put it all together. Oh, but first we need the parameters f and k. So f is the feed, so how much we're putting in, and k is the kill, which means how much is then removed, I guess you could say. I will also create parameters for this so we can access it from outside of the code box. So again, using a typical value for this, 0.055, and for k, 0.0662. Okay, this looks good so far. Okay, now we can work on this one. Again, we can say, okay, next A equals previous A plus, I'll put this into parentheses, plus dA times, here we have the Laplacian of A, so we can just say this is lab.x, because the X channel, so the red channel, always represents substance A, and the second channel, the Y channel, always represents substance B. So here, where was it? Here we have this, then we're subtracting the reaction. And then we're adding F times 1 minus A. This is just the previous A again. Okay. This should be fine. And then we have a similar thing for B. So this will be previous B plus also put this in parentheses, dB, which we have up here. Then again times the lab, but this time of Y, because the second channel. Then we're adding our reaction because it's plus AB squared. And here it also differs. So this is minus K plus F times previous B again. Okay, so far so complex, I'd say. We got an error. Is this an old error or is this a current one? Let's see. Oh, no, this one is still relevant. Am I missing something here? This looks good, this looks good. So opening, closing, opening, closing, opening, opening, closing, closing. Let's see. Okay, so it's not caused by these two lines. So it's probably up here. So nearest in 2 normalized coordinates plus vector minus 1, 0 times, oh, this is the culprit, I guess. Let's check again quickly. Oh, still. Okay, patch code outlet out of range. That's not relevant for now. That's just, I think that's related to how this is, how this codebox object is patched internally, but never mind. Okay. Where were we? Debugging. Okay, so the next thing is we need to clamp those values. So we don't want this to blow up. So we can say next A equals clamp of next A between 0 and 1. So these values will stay in that range. And next be same thing here. And then we can, let's call this one color. This is then our output vector, which consists of next A here as our X, next B as our Y, and Z value can just be 0. And then we can say out1 equals this color. But nothing will happen. It will just turn red because we need some kind of an initial seed, like we need to get this reaction going. And what I mean, you can use different kind of inputs. What I like to do is using a noise. So jit.noise, free planes, float 32. I don't know, let's do something like 160 to 90. I am, as always, running out of space. Maybe let's do something like this. Shifting this down a bit, okay. So every time we bang this one, we get a noise texture. Or no, now it's a matrix. We'll turn this into a texture, and then I will also, I create another jit.gl.pix to create some kind of a threshold here. So only if the input is bigger than, I don't know, 0.9 or 0.95, even bigger. So only if this is bigger than that number, something is coming through. Then I can take this as an input here. So let's shift this a bit. So every time we're banging this, we're kind of deleting what's coming in through the feedback and reassigning it. Okay, now you can see something is growing here. Now it's kind of slow. What we can do, for example, we can take the Uzi object, which will send out a specified number of bangs. So now we're banging it once every frame, but we could also say that we want to bang this like 5 times every frame or 10 times every frame, and then it's growing faster. But when you're doing this, you have to be careful of the frame rate. Okay. I mean, not much is changing now. This is I'm working on a pretty powerful computer, so depending on what kind of machine you're using, this can drain your frame rate. Okay, so this is essentially the main thing, the main code implemented. What we, of course, can also try is changing these parameters. But I mean, I would start with these values and then gradually change them because, where's the K? So it works with these values, but if you're changing them too much and if you're doing something too extreme, it might not work anymore. So let's change this one here. And we have something like that. What about this one? Okay, yeah, looks nice. Before we're moving on to the third part, which would be using a mask, I will quickly change the color because now, yeah, as we said, red is representing substance A and green is representing substance B. But we could also say, maybe we can use two outputs. So output 2 is just what's coming out of here, and output 1 is like the one where we change the color. So we could say we're just looking at the X component, so it will be black and white. But then I have to plug this in here. Yeah, so now it's black and white. But we could also use something like HSL to RGB to set the colors and say, okay, the X component will control the color, and then we'll have saturation and brightness of 0.5. And now we have something like this, or it could be 1 minus. Okay, 1 minus doesn't make sense because it's essentially this one. So you could do something like that. Or also apply some kind of a power function here. So it changes a bit. Oh, I think this looks nice. Okay, so I think this is working, so I can delete that now. Still doing a bit of tidying up. Okay, now we can move on to the third part, where I want to introduce some kind of a mask to control where the reaction is happening and where it's not happening. Okay, so the way I'm doing this, you could use different black and white textures. So it could be like an image. A video is probably not, I mean, depends on how you're tweaking the parameters, but with the video, there's usually this won't react fast enough. But I guess there should be some combination of parameters where a video would also work. But what I want to do is use a text. So to do this, I'll use a jit.gl, no, not texture, text object. Let's set the color to white. I don't know, font size 25. Align 1. I think this should be, okay, 0 is left, so I guess 1 is center. Then add font name Arial and yeah. So I don't want to draw this just to our world object because we're inputting the texture directly into this. So I will create a jit.gl node. So this is essentially another rendering context. Then let's call this one the text node. No, add name text node. And set the dimension also to HD. At depth 0 and at capture 1. So what capture 1 means, or what it does is, so if I copy this, capture 1 means that we're getting the rendered texture as an output here. So all we have to do now is say draw to text node. Okay, no, this one. So what do we have here now? We have a text that is rendered to this node, and we're getting it as an output here. So theoretically, if I didn't make any mistakes, if we say text Reaction-Diffusion, now we can see it here. So maybe we can change the font size a bit. Where is it? So we can do something like that. And maybe also make this bold. I think this would be, is it the weight? Yeah. Look at that. Okay. But there is one thing still missing, because with the mask I will use, or with the masking code, everything that is white here will have the reaction working, and everything that is black will have, we'll just stop the reaction. So I will use another jit.gl.pix, call this one invert, and just invert the colors. So whatever is coming in here, we're subtracting it from 1. Okay, so I guess this looks good. So what we can do now is introduce a new variable, call this one mask. This will be our input 3. It would be nice if we could see all of this at the same time. But can I pull it off? Okay, should be fine. Yeah, and then we can do the following here. When we're creating our final color, we can just say times mask, and this essentially means, okay, the whole feedback system is only getting applied on everything that is white in our mask. So then I can plug this in here. But where will this go? Okay. And now if I'm starting a reaction, let's make it a bit faster. You can see that it's applied everywhere but our mask. It looks also kind of fun changing the size. Maybe it would look good if it would cover more of our screen. So we could do something like this. changing the scale, and then also, oh, where is it? Changing the position a bit. Okay, so yeah, and then when we're changing our values, if we make this a bit finer, we also get the insides of our letters. Maybe we could say this also changes. Yeah. Okay. Very, very nice. Yeah, this was essentially what I wanted to show you. I hope you found this useful. Thanks for watching.